Yes, sir.
Taught the same course before, Dan? You teach the same curriculum that you done?
No, this is all fresh.
Oh.
And it takes me a lot of time to prepare the lectures.
How did,
When you upload like the slides to the web, could you, so any chance like turn on the handout slide? On the bottom?
If I figure out how to produce, yeah, there is a way to produce them.
Like slash handout and like, and when you like document class.
Okay,
And I like.
yeah,
Because there are like a ton of each of these slides, there are like 4 or 5 because the animation and stuff.
That's it.
So yeah, it's like
between that
like
and
20 like actual slides. So handout,
Where's your looking for? You can stream live on YouTube from your meeting. I'm just like amazed that you can stream live on the Twitch with via Zoom.
why don't we?
workspace for Meta.
I'm just amazed that you can just like stream.
Yeah, we should go.
We should go.
I think it should go.
Twitch learning TV theory.
every reviewer may say
Okay, so I think we are all set, and it is exactly 10 past the hour. If somebody here can check on Zoom that they see indeed a clean screen as we see here, so it's, nothing is covered. So today we finally give up on entropic inequalities for a while, until the end of the lecture, so not for too long. And we will start talking about a very classic and old topic, but super important topic in databases, namely constraints. We are going to cover today only the classical constraints. So functional dependencies, multivariate dependencies, and something that is actually not part of databases, it's part of graphical models, conditional independence constraints. And we will discuss the basics, trying to make it as sophisticated as it can get, and then describe a modern approach, which means using entropy vectors to reason about these constraints. And then next week, I'm planning to discuss the more general view of constraints, which are generalized constraints, tuple generating constraints, equality generating constraints, and the Chase procedure. So that's not going to be, it's going to be too complex to model with entropic vectors. We need to go back to logic. Okay, so let's start with functional dependencies. So this is a very classic topic. I'm going to go relatively quickly. So we fix one relation schema, so no instance yet. There are some attributes. And the functional dependency is just a piece of syntax that says a set of attributes determines another set of attributes for 2 sets of attributes, subsets of X. The semantics is that if we're giving an instance of this relation, then the instance satisfies this functional dependency. And I'm going to write like this: the instance satisfies sigma, and sigma is this functional dependency. If for any 2 tuples, if they agree on U, then they must also agree on V. Yeah, so we have a syntax, and what does it mean? It means that on a particular instance, 2 tuples that agree on U, they must also agree on V. We often have a set of functional dependencies denoted capital sigma. And then we say that an instance satisfies this if it satisfies all the functional dependencies in this set. Very basic stuff. Who never heard about this definition of a functional dependency? Who never heard about functional dependencies before? Okay, everybody, that's what I thought. So I had to prepare an example. It came out incredibly complicated and actually kind of useless. I will try to be clever here, and y has the first two digits and z has the last two digits of x. So you have 1, 2, 3, and then 1, 2 for y and 2, 3 for z. That is the rule. So what functional dependencies hold here? And it turns out they're actually quite boring. Of course, x functionally determines y, x functionally determines z. X also functionally determines the set yz. I wrote it here. X functionally determines yz, and the set yz functionally determines x. Yep. However, y by itself does not determine x. And we need to prove this. You find two tuples, the first one and the third one. They agree on y, but you do not agree on x. And that is that refutes this particular functional dependency. Very basic stuff. Okay, the interesting thing about functional dependencies is the implication problem. Given a set of functional dependencies sigma, we say that it implies another functional dependency small sigma if for any database, for any relational instance, if that satisfies big sigma, then it satisfies the small sigma. And we write this with the same turnstile symbol as that we also use for the satisfaction relation. So we say sigma implies capital sigma implies small sigma. Okay, so some short example. These two functional dependencies imply the third one. So a quick proof. How would we prove this? Well, we need to start from the definition. We imagine an instance. When we take any instance, it has many tuples. We need to check that this particular functional dependency is satisfied, assuming that the first two are already satisfied. How do we check that this functional dependency is satisfied? Consider any two tuples, here they are, that agree on A and on D. So I put here the same values on A and D. We need to prove that they also agree on E. Why is that? Why do they agree on E? Well, we need to use what we know. We know this assumption, which is not yet captured by my little figure. We know that AB implies C and that CD implies E.
Are you using B in the transition?
Maybe A, B, D.
Yeah.
Because you need B as well.
Yeah.
We're waiting for it.
Yeah, I finished the slide last night at 11:30, so there may be more of these things. Yeah, it means that you really understand the implication problem, so we can move on. Yeah, that's what you do. You reason one by one and prove that those are equal until you get what you need.
But then that is also a counter exam.
This-
These two functional dependencies do not.
That, yes. Good point. So what was I thinking here? Why is CAD? I think I want, yeah, I should have added here B. ABD implies E. And if we add ABD and I put here the same B, then how do we prove that? So then it's easier because then we use AB implies C to conclude that also C is the same. And then we can finally use CD implies E to conclude that E is the same. Okay, good, cool. So classic stuff, Armstrong axioms. They are widely known by people in industry who don't know much about database theory, but everybody heard about Armstrong axioms. They come in lots of small variations. This is my favorite. So the trivial axiom allows you, says that any set of attributes implies each of these subsets. Transitivity, which I like to write as clean as possible. U implies V, V implies W, then U implies W. To compensate for the fact that we insisted for such a simple transitivity, you add the splitting and combining axioms, which say that U implies a set VW, if and only if it implies both of them. This should be an arrow. Yes.
So what do you mean with this? You need the splitting and combining because the transitivity relation is just similar.
Yeah, I kind of rushed this, but you'll find on the web variations of transitivity, where here they use maybe a larger set than V, and yeah, and that's it. So they say U implies V, and VZ maybe what am I saying here? No, I think I got it wrong again. I don't remember the other variations. I've always used this one, and I know it's complete, and yeah, that's what I know. Okay, but here is an interesting point that I know very well. If you look at these axioms and now you want to use them, you're at a loss. How do you prove that a set of functional dependencies sigma indeed imply another functional dependency small sigma? Well, you can apply repeatedly these axioms, and it will terminate, but it seems unsatisfactory. We don't know how long it takes. We don't know if this is in polynomial time. By the way, what do people know? Is it in polynomial time? Can I check in polynomial time is the size of the set of functional dependencies sigma that this set determines small sigma, or is it hard?
Graph reachability?
Sorry?
Isn't this just graph reachability?
No.
It's a data log program, though, right?
It's like a data log program, yeah.
Graph under.
So it's,
But the nodes in the graph could be all subsets of variables, right? So that's well.
So it's not, it's slightly more complicated than reachability. It is like the alternating ACAP, like alternating reachability, because you can only, if you have a functional dependency with where the left-hand side has multiple attributes, then you must know all of them in order to compute the next one. That's the idea. And this is where the yeah, I shouldn't go back to the
Is the
splitting.
answer no, or is it we don't know?
The answer is yes. And here is a beautiful, much more beautiful and simpler way to reason about this. We use a closure operator instead of Armstrong's axioms. So we fix a set of functional dependencies, and then given a set U of attributes, its closure is defined to be the set of all attributes that are functionally determined by the set U, given sigma. Okay. Question. Does U plus contain U? Yeah, it should, of course it contains U because of the trivial axiom. So U implies itself. So U plus can only be bigger. Also notice that we will always write just U plus. Everybody does this, but this omits the fact that U plus depends on sigma, which is an important piece of information. And if you have two sigmas, you have to be very careful with your notation. Yes.
Is this single step closure or transitive closure?
It is a semantic definition. It's like defining reachability in a single line because you say everything that's reachable. This is what we define here. We didn't say yet how to get there,
Okay.
but this is what I want to discuss. So this is what we teach to the undergraduate students. How do we compute U plus given a set U? We start from U, so what do you think? How do we compute it?
Apply the rules.
Apply the rules.
Again and again.
Yes, so concretely, we look at all the rules in sigma, and if a rule has a left-hand side in U, then we add the right-hand side to U. And now U is bigger. I mean, we call it U plus, we don't call it U anymore. Now U plus is bigger. And you repeat, you look at another functional dependency in sigma, add that to U, and increase until there is nothing to add. This only takes polynomial time. Because every functional dependency only will be added at once to U plus. So this takes polynomial time. The second important observation is that computing the closure immediately helps us deciding the implication problem. Sigma implies the functional dependency U implies V, if and only if V is a subset of U plus. This is exactly by definition. U plus contains all the attributes that are implied by U. So this is why the implication problem is in polynomial time. How do we check it? We compute the closure of U, and then we check that V is a subset of U plus. Okay, so quick example. Again, I'm not proud of this example. For undergrad days, I have much cleaner examples, but I'm pretty sure some of you know actually more about function dependencies than I do. So what is AD plus here? Here I'm pretty confident what it is. What is it? Just AD, very good. What is ABD plus? Yeah, ABCD. And E. Again, I forgot E. I need to add E, yeah, because of this rule. Okay, good, cool. So this is the closure of. So here is an interesting. Yes, Remy.
Yeah, so I think I just read somewhere about you can compute the closure in linear time, but over a different end. So do you know anything?
But over a different one.
So here is E time over the side of the FD, and the side is measured by like the total number of variables. So I read somewhere, I think it's linear time, but maybe is it in the number of rules, or do you know what I mean?
It is exactly the alternating graph accessibility problem. Do you know what that is?
I don't know.
Good opportunity for me to not talk about the slides which have all these bugs, and instead show you the alternating graph accessibility problem. I need to stay here to make sure that. So the graph accessibility problem is we are given a graph G and two nodes X and Y. And the question is there a path from X to Y? Very simple. Actually, I should call them SNT, source and target. The alternating graph accessibility problem receives an alternating graph where the nodes are labeled or and. So they look something like this. This is an and. Maybe it has inputs A and B. Then there is an or, and this has an input C. And then there is, I don't know, there is another
Arbitrarily labeled?
They are arbitrarily labeled with, and let me stick that in, sorry, this is D. And I want this output to come here to make it cyclic. And the alternating gap accessibility problem says we are giving a source node or maybe several source nodes. Can you find an alternating path to a target node? How do you find this? What is the definition of such a path? Well, if you have an OR node, then it suffices to reach one of its children. If you have an AND node, then you must have reached all its children must be reachable before you can declare that this one is reachable. It's really like a circuit. It's the same problem as a circuit. If you interpret these nodes as gates and or gates, then you start by putting a one on these leaves, and you compute the circuit and to check that the output is 1. And if it's 0, then it's not reachable. What's the connection to functional dependencies? So let me take one of our functional dependencies. That one, AB implies C. It's not interesting enough yet. So let me give a more interesting one. AB implies C. Also AD implies C, and CE implies A. So I hope this is visible. Let's construct the alternating graph accessibility alternating graph accessibility problem that checks whether let's create a problem here. So now help me, something interesting.
So AB goes to an end node, right? Or no, are you saying?
And I want a question. I want to check if this implies something. What would be interesting? Let's say AE implies E. Actually, it's not. Yeah, but you know what? It's not super important. Would be the question. Let me construct a graph carefully. So the graph goes like this. I'm going to start from AB. I must have both of them in order to enable C. But I have a choice for C. I can also use A and D. And any of these allows me to conclude
C.
C, but where do I put C?
Leave another node on top.
Okay, so it means that I need to make. It's a but I want to be able to write this. So I think I want C to be this node.
Is it a directed graph then, or an undirected graph?
It is directed.
Okay, because
You would just have C as a single output node as well, right? Because if the OR node is reachable, then C.
I also want this CE. So if I have both C and E, yeah, you're right. Maybe I should do it.
You are doing a cycle graph with cycles.
Yes.
So then all the letters would appear here.
Yeah. So this. So I'm going to do this, and now what else do I need? C and E. C and E. C and E. Determines whatever D. That's my graph. So now we set to 1 whatever inputs we have. We compute the circuit and we see if D is set to 1.
Wait, it connects to C or it connects to the?
wait.
Or
To A, go to
It connects to
A.
A, not D, right? It connects.
To 8. You're
Like
right.
that, you could just create a guide, right?
Good. So getting back to Remy's question, what is the runtime that you need to compute the value of a circuit if you have if it's you know some of the nodes are labeled 0, 1?
Linear in the number of operators.
Linear in the number of operators.
But
Okay.
there is a cycle then, so it is not a cycle. There is a, is it obvious that you don't have to use the cycles?
I wouldn't go any deeper. So we can spend too much time modeling. I'm not completely sure I got it right. I'm a little bit troubled by the fact that we can both set these variables to 0 or 1 as we want, and they can also be set. Maybe that's correct, but you know I would need to think about this. Okay, good, cool. So let's continue. Should we? Because there are other things that are super cool that I want to show you. This is again a very well-known fact. The fact that if you have an implication that fails, then you can refute it using a relational instance that has only 2 tuples. Yeah, so I stated as a fact, if sigma does not imply lowercase sigma, then there exists a 2-tuple relation such that this relation satisfies all the functional dependencies in sigma, but fails to satisfy our consequence. Let's prove this by example. Here is a set of functional dependencies. They do not imply CD functionally determines A. I want to design a relational instance with just 2 tuples. This relational instance should be the witness that this implication fails. should be the one that refuses implication. So what would you place here? And I want to place only value 0 and 1, just for some discipline. How would you design these two tuples?
Actually, 0 and 1 for A.
For very good. So for A, we put a 0 and a 1 because we want this to be distinct. So with the same reasoning, what else do you want to do?
Just have C equals B.
We need to put here 0 and 1s. So what would you put?
1, 1,
1, 1, 1, 1 here.
You just need C and D to be the same, right? In the two tuples, it doesn't matter, it's symmetric.
Exactly. We must have C and D be the same. And the same, I'm going to choose 0, which is my own discipline. And A as a Remy set, we want A to be different. 1 will be 0, 1 will be 1. What do we do about the rest?
Satisfy those functional dependencies.
Exactly. So the disciplined way to go about this is to compute the closure of CD, because in the entire closure, these must be equal. They must all be 0. And A must be different, and A will not be part of the closure. Otherwise, we would have had the function dependency hold. And B can be anything you want, but if you also make it different, then you refute a stronger function dependency. You refuse the fact that CD does not determine either A or B. Yes, Remy.
So does it matter if we choose C and D to be the same or to be different? So here we choose both to be 0. So what if we put 0 and then 0 for C and 1 for D?
If you put it doesn't matter. So the values in each column, they can come from their own domain. Yeah. Okay. So the general rule is that if we want to refute a functional dependency that does not follow from our axioms, then we create two tuples. One is full of zeros, and the second one will have zeros for U plus, for the closure of U, and the rest will be 1. Okay, these two tuple relations, they also play an important role for entropic functions. Their entropies are very simple. Their entropic vectors are very simple. And the linear combination of these entropic vectors, they have been studied intensively. They form a strict subset of the entropic vectors. They are called the entropic vectors with a non-negative I measure. And we call them normal polymatroids or normal entropic vectors. I think it sounds nicer than with a non-negative I measure. My hope was to show them to you in this lecture, but I run out of slides and out of steam, so I can't talk about that. Maybe we pick this topic up later. Good. A cool concept that I don't think is widely known even by among database experts is the Armstrong relation. The Armstrong relation, let me justify it. So we just saw that in order to refute a single implication, we only need an instance with two tuples. But what if you want to refute all failed implications by a given set of functional dependencies? That is called an Armstrong relation. And it's remarkable that one exists. There exists a relation, I called it R sub sigma, such that the functional dependencies that hold in this relation are precisely those that are implied by sigma and nothing else. If you relax your logical constraints, then this no longer holds. Then for different failed implications, you need different models. But for functional dependencies, it holds that there is a unique model that captures all your implications. Is it clear what we expect from the Armstrong relation? Yeah.
So is this like sort of like a dual construction to the previous tuple example? Basically doing the opposite. You're demonstrating like everything in the relation is true and everything else outside of it is not true. Whereas previously we showed, kind of demonstrated the functional dependency was false by constructing an explicit counterexample.
Yeah, I wouldn't call it dual. It's really an extension of the same principle. So we constructed one small relation that refutes one consequence. Now we're going to construct a relation that refutes all the non-consequences of sigma.
Can you do this with alphabet size 2?
Sorry?
Can you do this with alphabet size 2?
No. But it's a good question. So we cannot do this with alphabet size 2. So I'm going to show you. And again, the more interesting part is actually the construction, the proof. Much more interesting than, I mean, the statement itself is also super interesting. Unfortunately, I forgot to prepare examples of logical systems where this fails. Maybe I'll do this for next week. Then you really appreciate why this statement is interesting. So the technique that is used to construct Armstrong relation, it's I found it introduced in a beautiful paper by Ron Fagan. It's called the direct product of two tuples. And in some recent papers, we use the same construction, and I just screwed up the name, and I called it domain product. So you might hear me talking about it either as a direct product or as a domain product, same thing. So here is a definition of the direct product of two tuples. We are given two tuples of the same length. Their direct product is a new tuple of the same length, where each attribute value consists of the pairs of the pair of values in the previous two tuples. Okay, so notice that the domain of this new tuple is neither the domain of T nor the domain of T prime, but it is the product of those domains. But importantly, they have the same length, and this is an important property. Okay, and this extends to two relations. If we have two relations with the same set of attributes, then their direct product is the set of direct products of the all pairs of tuples in the two relations. How big is the direct product of R and R prime? How many tuples do we have? As a function of the sizes of R and R prime.
Are you fixing an order?
What do you mean by order?
Order in the order of the tuples. Like the relations are not typically considered ordered, right?
No, it's like a Cartesian product. Exactly, it's like the product of the sizes of the two relations.
This definition, we haven't said that yet. We define it because Grace's definition could also be applicable.
I don't think I understood Grace's definition.
Because like, if there are tuples A1 through AN and B1 through BN, right? Is TX like T like cross T prime? Yeah. Is that of size n or is that of size n squared?
Okay, I see the confusion. When we look at the size of the relation, we count the number of tuples inside. We usually don't mention the size of a tuple. We sometimes say the number of attributes, but the tuple counts as one. It's one tuple. But we do care about the number of attributes, which is like the schema.
So it's actually size n.
These are attributes, and I wouldn't call it size n. I would say it has n attributes.
I think the confusion is because there's ambiguity in like A1, B1 to A and Bn. That might be A1, B1, A1, B2, A1, B3.
Got it.
It is A2, B2, but I think that's the
Yes. The tuples don't increase in size, but the relation is now like the cross product.
Yes, I agree. I'm just saying the notation is confusing.
I should have caught it. You're right.
It's almost the same thing, but it's the cross product and the concatenate operators are two different things. So you define the concatenate operator in the first two lines, but you hadn't defined the cross product operator one way or another at the bottom.
Yeah. So let me write it here. So A1, A2, A3, direct product with B1, B2, B3 is a tuple A1, B1. A2, B2, and A3, B3. Yeah, so
Concatenation in this book.
it's concatenation, but you put together the attributes. You want to have it the same number of attributes. Okay, so let me show you an example, not to be confused with the Cartesian product. This is what we do in databases. We think about the Cartesian product a lot. We never think about the direct product, although it's a very interesting mathematical construction. Here are two relations. Their standard Cartesian product will have size 6 because we have 2 tuples here, 3 tuples here, and their Cartesian product has size 6. The schema of a Cartesian product consists of the union of all the attributes in the two relations. And that's unavoidable. We need to include all these attributes. For the direct product, we cannot construct the direct product of T and S. They must have the same schema. So I'm proposing a second relation, R, that has the same schema with SS. And now their direct product is this one. It is so it has the same attributes X, Y, Z. And it's pretty much like the Cartesian product, but with the difference that we combine the values of this X with this X into a new value called value 1A. Yes.
So I'm taking the Cartesian product with R and S, and then I'm like zipping the tuples together.
Beautiful.
Oh, great.
That's a very nice mental image. We take the Cartesian product, we have some name clashes, and you smush together those name clashes. Okay, the interesting thing is that you can extrapolate properties from R and S to R join S. This is especially interesting for entropies. I can't give up, so I need to bring them up over and over. Imagine that you also have probabilities associated to these tuples. So 2 probabilities here, 3 probabilities here, they add up to 1. You know what a probability space is. It is natural to define a probability space on the direct product. How would we define the probability of one of these tuples? How would you naturally define it? Just a product of the 2 probabilities in R and in S respectively. It's like independence. Yes.
I haven't been here, so I apologize if I make you repeat yourself, but how should I interpret the problem? You just said that I want them to sum to 1.
Yeah.
What is the intuitive interpretation of the probability assigned to a tuple? It's not the likelihood that that record exists, because then I wouldn't have the rule that they sum to 1. What is the intuition for what it means to assign a probability to a record?
You give up the database U.
I will.
And you imagine a probability space in which you the outcome is one of the tuples in your.
Okay, that makes sense.
Yeah.
Thank you.
And this has great applications for the AGM bound for guaranteed upper bounds on the size of a query with an not immediately obvious math that you apply to get to those bounds.
That should be a 1A, by the way.
1A. It's 1A. You found another bug? Oh, right. This should be 1A. Yeah. So the interesting thing about the entropies is that the entropy of those the new probability space has the same set of variables X and Y. And you can now compare the entropy vector of X, Y, Z on the product space with the entropy vectors of R and S. They have the same dimensions, eight dimensions. And what is the connection? What do you think is a connection between the original entropies of, look at just R and S, and the entropy of their direct product? What is the entropy of 2 independent random variables? Sorry? Their sum. Exactly. The same applies here. The direct product is just taking independent outcomes from the 2 spaces. So it is a sum of R and S, but it's a sum in a very deep sense, in the sense that the entropy of X is the sum of these entropies of X. The entropy of XY is the sum of the entropies of XY. It's really a sum of 2 vectors. Completely different from talking, I don't even know how to talk about the entropy of the Cartesian product, because it's a vector that is unrelated to the previous vectors. The entropy of all 5 variables is indeed the sum of the entropy of AB here plus the entropy of XYZ. But as a vectors, they are not so nicely related. While here they are very nicely related. And again, there are some cool stuff I can show you about this, but I didn't put it on the slide. And
Why is this just not just like taking the Cartesian product and then applying a bijection to each row? I mean, that seems like the obvious interpretation. I don't understand what Steve did.
yeah, so this is what he said. So you can view this direct product by taking the Cartesian product and then zipping together the common values. It's very simple. The reason I insist so much is because it's simple and beautiful. And I want you to appreciate the beauty.
So where does that h sub t plus h of s term come from? Is that the improper vector for h of t process?
Yeah, so this is very bad. This is indeed a vector, and this is the entropic vector of here.
Okay.
This is bad. I shouldn't have written. I didn't know what to write here because you cannot ask. These are two different vectors.
Okay.
So here it only makes sense to apply to look at individual components of this vector. I need to fix this. This is not a good notation. It's not a good message. Yeah. So this is what makes the direct product so interesting. Its entropy is really the sum of the two entropies. Good. So let's continue. So Armstrong relations. So we have a set of functional dependencies, which I forgot because it doesn't show up yet. First dilemma. If we have a functional dependency sigma, then this functional dependency holds on the direct product, if and only if it holds separately in each of the relations used in the direct product. Now that you think about this, yeah? So let's prove one direction. If it holds in the direct product, why does it hold in R? Well, imagine two tuples in R, they agree on the left-hand side of sigma. So now we need to use this information. Use any tuple, fix any tuple in R prime, doesn't matter which one. Do the direct product, and the two tuples of the direct product of our two tuples in R with that unique product from R prime, they will also agree on the left-hand side of sigma. And therefore, they agree on the right-hand side, and therefore the two tuples in R already agree on the right-hand side. Very straightforward. Armstrong relation goes like this. We start with a functional dependency, set of functional dependencies sigma. And we are going to construct this relation that satisfies precisely those little sigmas that are consequences of big sigma. Here is how it goes. It's an interesting construction. We use in a significant way the fact that the number of functional dependencies is finite. So we can go over all of them and check if they are implied or not implied by sigma. The interesting ones are those that are not implied by sigma. For each of them, we constructed two-tuple instance, Ri, that refutes the implication of sigma I from big sigma. Yeah, so we have a small two-tuple relation that satisfies a big sigma, but not a small sigma. And now what do? Yeah, we just construct the direct product. Yeah, and this satisfies the theorem. I wrote there why, but I think it's obvious. Yeah, because
is there well, this is going to be huge. Is there some sort of like bound you can get on the sort of like the smallest?
Which reminds me, yeah, I have a question here. How big is it? 2 to the n. And I don't know. So actually, I learned about this from a paper by Perl and Geiger, who refers to Fagan, who did this for horn clauses. I never wrote the original paper by Armstrong, so I don't know the original construction. But to my knowledge, nobody worked on making it smaller. Yes, Joe.
Implicit here is that you've chosen a sigma, because there are many equivalent sigmas. So there's this minimal coverage thing, right, where you can get this sigma to be as small as possible. Yeah.
Yeah. So what happens if I choose a different sigma that is logically equivalent to my sigma?
Is the closure going to be the same?
Exactly. The closure is going to be the same. The set of functional dependencies implied or not implied by my first sigma or my second sigma will be the same. And the Armstrong relation will also be the same. The semantics of the functional dependencies is given by this implication relation. That is what is given. Does it make sense, Joe?
No, it doesn't, in the sense that the N here is gonna work out to be the same in both cases. I'm surprised. There's sort of some, for every two tuple that you introduce, you knock out some little sigmas, right? But
Okay.
my list of little sigmas can be quite different depending on which version of big sigma I choose, right?
Well, if you choose them semantically equivalent, the big sigmas, then they should have exactly the same consequences.
That I agree with.
And therefore, what you list here are as the non-consequences, so they must be the same as well.
I think you're saying it was redundant.
Yeah.
And this actually is an important message that I want to convey. Yeah,
This is the worst case N, right? N is gonna probably be smaller.
yeah, I agree. But again, I don't know of any work who looked into this deeply. I mean, from a theoretical point of view, the first question is an exponential size really needed, or could you? Yeah, can we prove that exponential size is lower bound? And I don't know. Good. So finally, we finally reached the end of this classical topic, functional dependencies. No, we did not reach the end of functional dependencies. I still want to discuss the closure operator. So the message I want to convey is that we should think about a set of functional dependencies semantically, not as a list of functional dependencies. This is what undergraduate textbooks have to do, because people then need to start from the list of given functional dependencies. But we should think about them semantically, and one way to think about them semantically is through the closure operator. So forget the original list of functional dependencies, but retains this function that computes the closure operator. The closure operator, you can replace it with something which is not a function, namely, you can replace it with a set of closed sets, which are precisely those sets of attributes that are closed, for which the closure operator is a thing. And this in turn defines a lattice. Okay, I didn't do a good job describing the motivation, but let me show you the details. Before I do this, here are the basic properties, actually the defining properties of a closure operator. In our case, our closure operator is that that comes from functional dependencies. But these turn out, we will use these as definition of a general closure operator. So, thinking about functional dependencies, monotonicity holds trivially. Yeah, if you start from a bigger set, then the closure will be bigger. The fact that the operator is expansive, we already discussed this. When you compute the closure, you include everything in you. Here is a fun fact. This is something that theoreticians like a lot, and practical people see this is a waste of time. If you apply the closure again, why would you ever do this? But if you do it, then you don't get anything new. So it's called idempotence. And notice that these are the terms that I typically use: monotone, expansive, idempotent. I checked on Wikipedia. They call it increasing, extensive, and idempotent. Yeah, so terminology might differ. Okay, so these are the properties to keep in mind. So I want to spend this slide to tell you that the notion of a closure operator and its associated closure system, which I will describe in the next slide, these occur in very, very many places in mathematics. For example, for getting functional dependencies, think about sets in a d-dimensional space. And define the function that takes a set and computes a linear span, which means the smallest vector space containing S. You start from a set and you expand it to a vector space. This is a closure operator. It is monotone. You give me a bigger set, I'm going to give you a bigger vector space. It is expansive, and it is idempotent. If you do it twice, you get the same vector space. The convex closure is also a closure operator. Start with a set, compute its convex closure. The topological closure of a set in a topological space, like an R to the D, is also a closure operator. And in any algebra, the algebra generated by a subset is also a closure operator. The message I want to convey is that this closure operator is really occurs in very many places in mathematics. So here is what you need to know about the closure operator. This is really fundamental. So the closure operator will be defined over a set omega, and it is really a function from subsets of omega to subsets of omega that is monotone, expansive, and idempotent. The things that you need to know is that this is equivalent to what is called a closure system. A closure system is a subset of the subsets of omega that has a property that for any subset of this set C, the intersection of all the sets in S is also in C. Let me use terminology. We call the sets in C, we call them closed sets. And the property that this set needs to satisfy is that the intersection of any set of closed sets must also be closed. These two definitions are equivalent in the following sense. First of all, if we are giving a closure operator, we can go back. If you are given a closure operator, I can define in a very natural way a closure system. How would you do this? How would you define the so-called closed sets? By just looking at a closure operator. When do I call a set? How did I call it? And I want to go back. I called it A. How would you call? When would you call a set A? And a subset of omega called it A. When you call it closed? When it has what property? Sorry? Yeah, it's like a fixed point you wanted to say?
It's equal to its closure?
It's equal to its closure. So the closed sets, oh no, I got the opposite. Okay. Yeah, I did it. So here it is how we define the closure system. So we are given CL, and the closed sets are precisely those sets X for which the closure is equal to X itself. Yeah. In the opposite direction, if we are giving a closure system, how do we define the closure operator? Well, given any set A, its closure is going to be the intersection of all the closed sets that contain it. And this intersection is closed because of this property here. The first bullet doesn't require any proof. The second one does require a short proof, and I have the proof right here. But I think I should skip it, although it's super elegant. I don't know how. Let me skip it and we'll come back to it if we have time. Okay, so we are back to functional dependencies. So we know how to construct a closure operator from the functional dependencies. This immediately gives us a closure system, namely the closed sets. And since these sets, the closed sets, are closed under intersection, they form a lattice. How many people here do not know what a lattice is? Okay, everybody knows. A lattice is a set with two operations, meet and join. The lattice of the closed sets of attributes has a meet defined as the intersection, which is still closed. And the join, we can't take the union. The union of two closed sets is not necessarily closed, but we take the union and then we close. And that is the meet and the lattice. Okay, so here is an example. Here is how to think about the lattice. Here are two functional dependencies over 4 attributes. And normally, if you construct the full lattice of all subsets of these four attributes, we need to get 16 sets. But the lattice of the closed sets is smaller. And it has, you know, an interesting structure, I would say. So what is missing from here? For example, we do not find the set XZ. You look for XZ, it is not here. Why is XZ not here? Is XZ closed?
Preconditional. Nothing, so thank you.
Yeah, it has to be closed. If you wanted to say something. So what is the closure of XZ?
XZU.
XZU. So if you're looking for XZ, you better look here at XZU. So defining a lattice over the subset such that its meet is equal to the intersection is yet another way to present a set of functional dependencies. It's an equivalent way to present a set of functional dependencies.
So where is YU implies X in this graph, in this lattice?
Yeah, it's very hard to trace it down, but you can trace it by observing that YU is not present. YU is not present, and therefore you need to look for YUX, which is this one. Here is a more interesting question. Suppose I don't give you the functional dependencies, I give you this lattice. Can you write down the functional dependencies that define this lattice? And this kind of goes back to Joe's question. If we have two different presentations of functional dependencies, how do we think about this? It's horrible. You read the textbooks and it's a lot of time is spent on this. But you know, there are canonical alternative ways to describe it. The lattice is one of them. So what do you think, Connor? How will you go about finding the functional dependencies that define this lattice?
If you look at the least upper bound of any subset of the atoms, then that's everything that's implied by them.
You can take the atoms. The atoms are the ones that sit right above the empty set. You can take any least upper bound of a subset, like say XUY. XUY. This brings me here. And now, how do I read from here a functional dependency? This is not how you do. Here is what you do. You look for sets that you do not find here. And you list all of them. So what don't you find? There should be 16 sets and we have only a subset, so many are not present. For example, XZ is not present. XZ is not here. So it means that the closure of XZ is not XZ itself. How do you find the closure of XZ? If you don't see the function dependency, you just see this. What is the closure of XZ?
This is the least upper bound of X and Z.
Exactly. It's the smallest set in this lattice that contains X and Z. We know there is a smaller set because if you take all of them, their intersection must be also in this lattice. So here it is. It's here. XU, and this tells you that you need to add what functional dependency?
XZ implies U.
XZ implies U. You go over all of them. You add all of them. It's going to be redundant, probably, but the lattice is yet another equivalent way to define the functional dependencies. Yes, Joe.
Presumably, the order in which you resolve these determines the set of FDs that you.
Exactly. The order in which you resolve these will affect the final FD that you emit. Good, cool. So finally, this is my discussion. So functional dependencies are really a key concept. It's not just in databases. You talk to people who have no clue about databases, but they know what a functional dependency is. I just remember, I forgot to put it on the slide. There is an important concept called a key. What is a key? Given a set of functional dependencies, when do we call a set of attributes a key? When its closure is a set of all attributes, and according to the textbooks, that's not enough. It has to be minimal such. Otherwise, we call it a super key. And I know this because this is how I teach. Yeah, so keys are also widely known, super important. Function dependencies are super important. The classical stuff, which I didn't cover, but this is mandatory in any undergraduate class, we need to discuss database normalizations, Poisson normal form. I skip 3NF because I don't understand it. And in databases, key and foreign keys play a super important role. They are so-called semantic pointers. They are kind of pointers to another table, and you can look at them and they have a semantics. They are not binary pointers. And more recent people have looked at interesting applications like mining functional dependencies from the data, mining approximate functional dependencies, doing data repairs for functional dependencies. There is a beautiful, beautiful paper written by no other than Sudeepa, who sits right here, on a dichotomy for repairing a table that fails to satisfy functional dependencies. You need to remove tuples until you satisfy the functional dependencies. Is it easy to find the smallest number of removals? Well, it depends on the structure of the functional dependencies. And I hope to have time to prepare that for next week. Since you're here, I might actually ask you for some help. Okay, so that was my spiel about functional dependencies. Let's move to an esoteric topic, multivariate dependencies. Does anyone here teach multivariate dependencies in the undergraduate class? I don't teach it. Sudeepa, you're a hero. Okay. It's a topic that we don't really like to talk much about. But I will show you a cool angle to multivariate dependencies. First, a definition. And to justify it, we need to recap a classic notion, which is that of lossless decomposition. Here is how we get to lossless decomposition. Take a relation R and partition all its variables into 3 disjoint sets. Their union is a set of all the variables. And what we want to do, we want to replace an instance for R with its two projections on U and what did I do here? On UW and VW. So I choose W as a common one, which worries me because later I used U as a common one. Anyway, there are 3 attributes, and I'm going to use 2 in each of them. One set is common. My question is, can we always recover the original relation R from the join of the 2 fragments, R1 with just UW and R2 with VW? And the answer is no. What happens? What is the connection that always holds between the original relation and the join of its 2 projections? Subset. Which one is a subset of the other?
R is a subset of the cross.
R is a subset of this. But often this join has so-called spurious tuples, and then we don't recover it. Okay, so in general, this holds. So we call this as decomposition lossless if R is indeed a join of these 2 projections. That's a lossless decomposition. And something that every undergraduate student learns is that if a functional dependency holds from U and V, then here is where I screwed up. U should be the common set of variables. And if the functional dependency holds from the common set of variables to one of them, then the decomposition is lossless. And this is a fundamental property used in all this normalization theory. However, this is not a necessary condition. You can have lossless decompositions without the function dependency holding.
Is this sort of the ideal case from the talk yesterday?
Yes.
Ideas?
The ideal case from the talk yesterday.
So the talk yesterday talked a lot about multivariate dependencies. Okay, I just wanted to justify multivariate dependencies using this decomposition because this is exactly what they say. A multivariate dependency is piece of syntax, and a relation with variables u, v, and w satisfies a multivariate dependency if its projection on uv and its projection on u and the rest of the attributes form a lossless decomposition for R.
Where's the W in the syntax?
That's the point. It's nowhere, and I hate it. So instead, I always want to write a function dependency like this. Because the W is implicitly the rest of the attributes and is omitted. I have no idea why I don't know the history of multivariate dependencies, why they came up with this notation. But actually, we have a hunch, right? If the functional dependency holds, then the multivariate dependency holds as well. Okay, there is an alternative definition, and it's a mouthful, but it's actually quite easy to understand. It says that for any two tuples in R, if they agree on U, then what happens is that you must find a third tuple in R that mixes and matches the V's and W's from these two tuples. If you find it ugly, you're in good company.
Should that be W1? Sorry. The first W.
This should be W1. Yeah, sorry. Yeah, V1, W1, V2, W2. And then you're looking for V1 with W2. And by symmetry, you're also looking for, you must also find V2 with W1.
This is the intuition by the name. This is where the name multivariate dependency comes from.
Yeah, because of the set, right? So for a given U, the set of V's is kind of the same, but it's the same orthogonal to the W's. Okay, so I wrote this as a little puzzle. So if Z functionally determines X, what did I write here? Oh boy, then Z multivariate determines XY. This should be Z here. So why is that? Because of the decomposition. If the functional dependency holds, then it means that we have a lossless decomposition, and by definition, it means that the multivariate dependency holds as well. Let's see an example where the opposite does not hold, where you have a true multivariate dependency, and they are kind of long to describe. It's easier to see if we condition on nothing on the empty set. Then what this means is that we want the relation to be the Cartesian product of two relations. That's what a multivariate dependency says. Yeah, so I try to give you here a hint for a true multivariate dependency where Z multivariate determines X and Y. So this means that for each Z, the subset, that corresponding subset is a Cartesian product between X and Y. You see, for Z equals M, for Z equals M, boy, what did I do here? This should be M. This should be M, and then for Z equals M, the relation is a Cartesian product between AB and XY. While for Z equals N is a Cartesian product between just X and A. Notice that, yeah, is it clear what a multivariate dependency is? It's a very brittle notion. If you have a table that satisfies a functional dependency, what happens if you remove a tuple from that table? Does it still satisfy the functional dependency? No, not a multivariate, standard functional dependency. It still holds, but not so with a multivariate dependency. If I remove the first tuple here, then I break that Cartesian product and it no longer holds. It's a brittle notion. But it's interesting because it is a lossless decomposition property, just written in a different way. Okay, so theoreticians, they got a handle on multivariate dependencies, and the question is, how do we check the implication? And sure enough, Berry and others, I don't remember if this, yeah, it included Fagan, 4 authors, they came up with a complete axiomatization for multivariate dependencies and functional dependencies taken together. And I took this from their paper, and they are very complicated things. It's impossible to make sense out of this. And don't worry, I hope to show you a different approach to reason about the same things that is much more appealing. Okay, good. So I need to mention the limitation of multivariate dependencies as they talk about all the attributes. You can also consider multivariate dependencies on a projection of the relation on a subset of attributes. If that holds, then it's called an embedded multivariate dependency. And I don't have an example here, but imagine that your relation has more attributes than UVW, and you're checking only in the projection if this embedded multivariate dependency holds. It turns out that reasoning about these, it becomes much harder. There was a breakthrough result by Herman in 1995, who proved that the implication problem for embedded multivariate dependency is undecidable. The reason I bring this up is to emphasize this restriction of multivariate dependencies. They have to talk about all the attributes, not about a subset of attributes. Good. So that is all I wanted to say about multivariate dependencies.
John, that theorem is also follows that the implication problem for conditional independence is undecided.
No, it does not follow. The reason is because that problem does not agree with the implication problem for multivariate dependencies.
Yeah, but that problem is undecided, the conditional independence.
I know the story and I have it on the slide. So it was announced last year, and I don't know the status. I don't know if the papers were accepted and checked. There are two independent claims for that result. And they were announced at our Dagstuhl workshop. So I was so proud. I didn't have any contribution, but I can claim at our Dagstuhl workshop, both these results were announced. So what is that conditional independence implication? Before I go there, let me mention that multivariate dependencies are used to define what's called the forced normal form. I have no idea what that is, but it exists. There is also a fixed normal form. And obviously, there is no lattice, there is no closure system that allows us to reason about multivariate dependencies. It makes them so unsatisfactory. Good. Let's talk about what Sudeepa mentioned, conditional independencies. These do not come from databases. They come from knowledge representation and probabilistic reasoning. So now we start with a joint probability distribution over a set of variables X. As database people think about a table, and each tuple has a probability of being selected, these probabilities add up to 1. So we're still within a database framework. And we say that two random variables are independent conditioned on U if, so don't read this yet, if the following holds, the probability of VW conditioned on U is equal to the product of the two conditional probabilities. That's what we want to say. And we write it like this. V is independent of W conditioned on X. The problem with this definition is that it requires us to divide by the probability of U, which might be 0. So to be safe, you might want to expand it into this longer expression, but that's equivalent to this conditional. Okay, so everyone is happy with the definition of conditional independence. Okay, so here is a short example. X and Y here are independent random variables. And why is that? Because they are the product of two independent random variables. X with probabilities 1/3, 2/3, and Y with probabilities 1/2. When you multiply them, you get exactly these probabilities. Now, if you have a conditional, then you need to reason separately for each value of the variable on which you condition. Okay, but again, it's a brittle notion, pretty much like the multivariate dependencies. Namely, if you alter the probabilities, especially if you remove one of the tuples, then forget it. They are no longer independent. What is the connection between between conditional independence and multivariate dependencies? Any guesses?
Over uniformity.
Right. So we get there, but there is an obvious connection, that one implication that is obvious even from this slide. If you look at this one, what can you conclude about the multivariate dependency? Empty set multivariate determines y semicolon x semicolon y. They have to be the Cartesian product of these two outcomes. This is what I should say. Once you are no longer the Cartesian product, it's immediately obvious that they cannot be independent random variables. Okay, so in one direction, it should be trivial. If the conditional independence holds with its associated probability distribution, then the multivariate dependency holds as well. And now comes the question. So this was, to my knowledge, this was introduced by Judea Pearl. It's a very natural question. Given a set of conditional independence statements, that certain random variables are conditionally independent, can we conclude that another conditional independence statement also holds? He wrote a beautiful book, and I forgot the title. It has a long title, but it's a mandatory read, a book from the late 80s or early 90s on reasoning, probabilistic reasoning. It's just a charming book to read, and you learn a lot from it. And he describes this problem for all possible angles. And the big question is the conditional implication problem decidable? This was open for decades, and as Sudeepa mentioned, last year, two independent groups of authors announced that they proved undecidability by doing completely non-trivial extensions of Hermann's proof. However, Geiger and Pearl proved that there exists an axiomatization and therefore a decision procedure for saturated conditional independencies, which are conditional independencies that refer to all the variables. Okay, so if you refer to all the variables, then you really have an associated multivariate dependency. If you don't refer to all the variables, then you are related to an EMVD, and it turns out that the implication problem differs between embedded MVDs and the conditional dependencies, so all hell is loose over there. This is why this statement required a completely different proof from that for embedded multivariate dependencies. Okay, so there is this uneasy connection between MVDs and conditional independencies, namely that the MVDs correspond to the so-called saturated conditional independencies that refer to all the variables.
So then Pearl's proof is redundant to Bayes. Geiger and Pearl saturated CIs a reframing of Bayes proof?
Yeah, I didn't get a chance to read it. I read this Pearl paper a couple of years ago. They were aware of that, and I don't remember if their conclusion was that these are the same axioms or different. I just don't remember. But they were aware, and this is where I learned about the Armstrong relation. They proved that the saturated conditional independencies, they also admit an Armstrong probability distribution, if you want to call it this way. And it's exactly the same product. The direct product, you just put the probabilities there. It's the same, exactly the same construction. Yeah, so there is a very interesting connection, but it's an uneasy connection because it breaks for non-embedded ones. Yes.
So the conditional inferences are more general than embedded MVD because in safe semantic, every tuple has to have the same weights. Whereas for conditional independences, you can vary the weights.
Yeah.
So conditional independences are more general.
Yes. And this brings us to the next topic, namely the connection to entropies. I know, I'm aware I have 3 more minutes, but I only have like three slides because the connection is very simple. This is an observation that is due to Tony Lee, 1987, and he observed 2 things, namely that if you have a relation that satisfies functional dependency, then no matter what probability distribution you take on this relation, there will be a functional dependency, which means that the conditional entropy will be 0. Yeah, very straightforward. And he then observed that if you insist on the probability distribution to be uniform, then the multivariate dependency holds. if and only if the conditional independence holds between these attributes viewed as random variables, which means that the mutual information is 0. But this only holds if you start with an uniform distribution. So here, if they are uniform, we have both a multivariate dependency and the conditional independence.
Should be empty set instead of Z, sorry.
This should be right. This should be empty set here. And this is correct here, but except it needs to be empty set. If you alter these probabilities, then all hell is loose. The multivariate dependency still holds, but as Sudeepa pointed out, you can have this no longer holds. Good, but what this means is that we can approach the implication problem by using entropic inequalities. And this is the last thing I want to show you. And so I want to show you this on one of those bizarre examples, the union axiom from the paper by Berry and the others. Here is the axiom as written in their paper. If we expand it to include all the variables, we need to talk about the other variables, the unnamed variables here called Z. And you just write down the implication from the Berry's paper, but now expanded to expose all the variables. So this can immediately be converted into an assertion using entropic vectors. If these two mutual informations are 0, meaning that these multivariate dependencies hold, then it must be the case that this mutual information is 0 as well. This is what we have to prove. How do we prove these conditional implications? We haven't looked at them, but there is an easy shortcut. We prove an inequality. We prove that the sum of these two mutual informations is greater than or equal to the third one. And I claim that this suffices. If this holds, then this implication holds as well. Why is that?
0. It'd be negative.
Because exactly, this is an important observation because mutual information is greater than or equal to 0. So if both of these are 0, then their sum is 0, and therefore this one is less than or equal to 0, but it can't be negative, so it must be 0. So this is what we need to prove. So last night, between 10 and 11:30, I spent incredible, this was my third attempt. I tried other axioms, and you just expand it. And in the end, what the unsatisfactory thing is that it's actually, you apply some modularity, which is what you should do, but you also ignore some terms. Yeah, so they are very weak, kind of very trivial inequalities. They are so trivial that I didn't see them at 11 o'clock. It took me the third attempt. I was hoping for something more interesting, but they turned out to be trivial. And that's it. So thing to remember, every FD or MVD implication problem can be derived from a Shannon inequality. This is not obvious. It corresponds to a conditional implication of Shannon of entropic terms. The fact that it corresponds that it is equivalent to inequality inequality requires a proof. It is a non-trivial proof that actually fails in general. It doesn't hold for non-saturated conditional dependencies, and that was shown in a paper that blew my mind by Kached and Romashchenko, and they proved that Anyway, I should skip this. The thing to remember is that all those complicated implications can actually be derived by if you just apply some modularity. Until the end. Okay. However, these entropic methods, they are limited only to functional dependencies and MVDs. In databases, we care about much more interesting constraints, and that's going to be the topic for next week. No more entropies, but more logic. Okay, good folks. So I see you then on Tuesday. I'm happy to take any more questions if you want to hang around, but I'm already 2 minutes over time. Okay.
I think even with cycles, this is linear because, like, let's say if I say set data one,
Let me just stop the video, otherwise I have to cut too much.
I think it'll come out here.